It's great to have you all here. Today it is my pleasure to welcome Dr. Rudy Geelen from the University of Texas, Austin. Quickly, first I want to introduce the seminar series. We have 4 talks. This is the second talk of the 4. The next ones coming up are from Professor Katrin Dörfler about collaborative construction, and also from Dr. Christoph Weibel about powering the city, simulation, optimization, and machine learning. There is also a YouTube channel. If you missed one of the talks, there were already some last semester, you can just feel free and look them up online. This is our team, 4 people organizing the seminar series, me on the very right end, then Danielle, who is also here, and Dr. Mittenberger and Dr. Kraus, who are also helping. So, as I already mentioned, today Dr. Rudy Geelen from the Odin Institute of Computational Engineering and Science will present his work on learning physics-based reduced order models from data using nonlinear manifolds. And he is a postdoctoral researcher working with Professor Karen Wilcox. Before joining University of Texas in Austin, he received a PhD in mechanical engineering from the Duke University, and before that he had a Master of Science and a Bachelor of Science in mechanical engineering from the University of Eindhoven. And in his research, he focuses mostly on computational mechanics, reduced order modeling, and scientific machine learning, which is why we think he fits very well into this Design++ network. So for this talk, I want to briefly introduce what he's going to talk about before he gives away the topic. So it is about a novel method for projection-based reduced order models of dynamical systems. And with this novel method, he uses manifolds which are learned from a general representation learning. And he showcases this novel method and its generalizability and accuracy on different numerical examples, which are all nonlinear. So with that, I would like to give the stage to you, and thank you very much for joining us here.
All right, thank you so much for the introduction, and thank you so much to the organizers for having me here in Zurich to talk about my work. So today we'll be talking about how we learn from data these physics-based reduced order models using nonlinear manifold constructions. I do want to apologize before we get started on the heavy use of mathematical notations in this presentation. So unfortunately, this is quite necessary to really get to the bottom of showing you how and why these approaches work the way they do. But nonetheless, I've tried to keep it light and wherever possible, tried to include some toy problems or some at least visual representations of why the problems work. Then let me also acknowledge my collaborators on this project. First, we have Laura Balzano at Michigan and Steve Wright at Wisconsin-Madison, both of whom are numerical optimization experts, and they really helped me with some of the mathematical analysis and the algorithmic developments I will be talking about today. And finally, we have Karen Wilcox, who is the director of the Odin Institute, and who also happens to be my mentor currently as a postdoc. We'll start off with a little bit of background information on some of the work I'm doing. Then we'll move on to the data-driven learning of these manifold constructions. Then we're going to switch gears a little bit and show you how these manifolds can be leveraged in the context of physics-based reduced order modeling. I'll give you a demonstration of the approach, and finally, we'll finish up with some concluding remarks. We start off by acknowledging that physics-based models, they're very powerful and they bring in a lot of predictive capabilities, but generally speaking, they're very computationally expensive. So these graphics are just some snapshots from my PhD work at Duke, which was really on developing computational models for better understanding failure in materials and structures. And one of the things I found myself doing, especially in the later stages of my PhD, is that I have this model which has some inherent parameters. I had to fine-tune it a little bit, take the simulation, put it on a cluster, obviously simulation take a good amount of CPU hours, download the results, and then process everything again, and then do the same thing all over again. So for all practical purposes, this is not a very efficient workflow. And this really made me appreciate this concept of data-driven learning, or scientific machine learning, if you will. And specifically, what I want to talk about today is one subclass of these methods, which is reduced order modeling. And the context is as follows. We have a high-fidelity physics-based simulation model that comes to you in the form of PDEs or ODEs that can be solved on a computer. They're very large in dimension, so solution time for these types of problems ranges from hours, days, weeks, if not longer. And to that, we now want to build a reduced order model that is obviously much decreased in dimensionality and therefore also computational complexity, but at the same time provides a very good approximation to the results one would obtain with the high fidelity model. Obviously, because of the reduced dimensionality, these reduced order models solve in a matter of seconds, minutes at most. And obviously, there's tons and tons of methods that share aspects of this philosophy, but today we're going to focus on projection-based model reduction. And all these approaches typically follow these 3 steps to certain degrees. So we start off with training a model. So what we do, we end up solving a PDE model to generate a bunch of training data that we're going to refer to as snapshots. We then identify the structure of the model, right, by computing a low-dimensional representation of the training data. And then in the final step, we do the reduction, for which we do projection of the PDE model onto the subspace, the representation we have identified in step 2. Okay, so now let's talk about data-driven learning of these manifolds. So to start off, we're actually going back to plain old principal component analysis. And typically, in engineering circles, we refer to this as proper orthogonal decomposition. Now, there are some minor historical differences, but for all practical purposes, these methods are really considered to be equivalent. And it works as follows. So we have a representation of the state, which can be a pressure field, temperature, displacements, physical variables. That depends on a parameter t. It can be time, it can be something else. That's approximated by the product of v and s hats, where v is a basis matrix, and s hats are the reduced state coefficients. Now, if we do a projection of your original high-dimensional system states onto the linear subspace, there is a projection error, the epsilon j's, associated with that projection. And actually, you can quantify it as follows. You can take the singular values of the data squared, going from r+1 all the way up to k. And typically, for a lot of problems, this projection error is actually kind of large, which really diminishes the value of principal component analysis. Obviously, there's many alternatives for nonlinear dimensionality reduction, like locally linear embedding, multidimensional scaling. More recently, people have started using variational autoencoders and techniques of that nature. What I want to talk about is a fairly straightforward extension of the POD. And again, we consider system states, S, that now are equipped with a linear component and a nonlinear component. So the linear component is essentially, again, plain old proper orthogonal decomposition. But now to that, we add a nonlinear part that is comprised of a V bar, which is an additional basis matrix, this psi matrix, which are a set of coefficients, and G applied to S hat, which is essentially a polynomial representation of the projected training data. we have to do something with our basis vectors, and what we just define is we're going to state that these form orthogonal sets. And you can kind of summarize it by means of the following constraint set. So that is something we're going to enforce upon this problem. So then the question is, okay, you just added a bunch of nonlinear stuff to this approximation. Like, how do you calibrate it? How do you learn it from the data? And to do that, we're going to pose this as a representation learning problem. Now, in the machine learning community, they often call this manifold learning. But to me, as an engineer, the representation terminology is a bit more intuitive. So what we're going to try to do is we're going to try to minimize this objective function. And then again, looking at the previous slide, this is essentially the left-hand side of this approximation minus the right-hand side, such that this constraint set is satisfied. Now, typically, it pays off to have a little bit of regularization in there to kind of balance the magnitudes of these coefficients. So we add this Frobenius regularization term in here. And this is really the representation learning problem, which is at the core of our methods. So now we have two methods of solving this. I'm going to walk you through that step by step and really give you examples of how it really plays out for some of these toy problems. So first off, we're going to approach this problem through the lens of the proper orthogonal decomposition, the POD. And actually, there's a little bit of cheating because we're not actually directly tackling the optimization problem, but nonetheless, this is a really intuitive choice for a number of reasons. So we're going to start out with follows. We're going to take a data matrix S, that comes to you from your physics-based models. We're going to compute the singular value decomposition, as we all know, which is a very common matrix factorization. And the first R, leading principal components, we're going to define that to be our basis matrix V. The additional basis matrix, V bar, are then formed by the following Q left singular vectors. In step 2, we compute a representation of the training data in our low-dimensional coordinate system, which really just amounts to projecting it as follows, with the V transpose applied on the snapshot data for all the snapshots. And then in the final step, we have made an informed choice for the basis. We know our reduced state representation. So this whole representation learning problem simplifies into linear least squares. You can do this in MATLAB. It takes 2-3 lines of code, and that's it. And by taking the normal equations of this system, you can actually explicitly write out the solution of what that coefficient matrix has to be, such that we satisfy the representation learning problem in the least square sense. So in here, everything is known. We know the V and the V bar. The I is an identity matrix, and the W we have introduced as this additional data matrix in which contains all these polynomial representations of the reduced state coefficients. Okay, a lot of math up to this point already. Let me give you a very simple toy problem. We have a trajectory in a 3-dimensional space that we're going to try to approximate with only 2 degrees of freedom, 2 coefficients. So we have cosine t, sine t, cosine 2t over 2. We take t in the range 0 to 2 pi at 100 samples, and this is our data matrix. Now we're going to try to search approximations of the following form. So with the PCA, you end up with this. So we have an SREF, which can be initial condition or the mean state of the system, whatever you choose it to be. And then we have V1 as 1 hat, V2 as 2 hat. 2 basis vectors, 2 degrees of freedom. Very intuitive. With the manifold approach, we have the following. We have an additional basis vector that we can account for, that we can include in the approximation. And we have S1 hat squared, S2 hat squared. So only quadratic embeddings. Note that both these approximations only have 2 degrees of freedom. There's only S1 hat and S2 hat, nothing else. Now the question is, how do you calibrate? How do you learn? What do these scalar coefficients, xi1 and xi2, have to be? And this is what it really looks like. So in the black dots, you see the trajectory, which is inherently three-dimensional. If you do an approximation in a linear subspace, as one would do with PCA, you see that the blue curve is really not all that close to the black curves. The projection error here is about 40%. With the manifold approach, what it will do is it will take that linear subspace and apply a curvature to it such that you are much better suited for applying regression for this problem. And this approximation is a lot closer to the ground truth than you're able to do with PCA. And the only thing we needed to do to get that is derive two scalar coefficients, which happen to be minus 0.19 and 0.88. And that's it. We have a second approach that has been proven to be quite useful for more complex problems, which relies on alternating minimization. And this is really a more credible way of directly tackling the nonlinear constraint optimization problem. And it has the following steps. We start off by taking initial guesses for the coefficients and the reduced states, the xi's and s hats. So the only thing that's left to do is somehow infer from the data your basis vectors, the v and the v bar. And it turns out this is called your orthogonal percussus problem. And this is a well-known problem in matrix approximation literature, and it has an analytical solution given in terms of an SVD. So again, this is something we can do very efficiently using computational methods. Once we have inferred an update for the basis, we still use the initial guess for the reduced states. We can once again approximate the coefficient matrix. That's exactly what we've done before in approach 1. And again, this has a closed form solution, which is low dimensional, can be solved in fractions of a second. So now we have updates to the basis, we have updates to the coefficients. The only thing we now need to update is the reduced state representation of the data. And it turns out this is just another nonlinear least squares problem. There are no constraints here by virtue of the basis being solved by means of the orthogonal percussus problem. So the constraint kind of drops out from the formulation. And this can be solved using off-the-shelf solvers built into NumPy and MATLAB, whatever you feel like using. So for this whole approach to be kicked off, we need to have initial guesses. These are readily available in our PUD-based representation learning approach. So that's something we can use. And obviously, there's an iterative process, which means that we have to define somewhat of a stopping criterion. And we just look at the projection error invoked by a number of degrees of freedom and basis vectors. And we define a tolerance for that. So let me show you how approach 1 and approach 2 are different. And we go back to a little toy problem that is now formulated slightly differently. So we have a three-dimensional solution manifold, x, y, sine x, cosine y. Again, we sample it by sampling x and y in a range 0 to 4. And we then search approximations as follows. So for POD, PCA, it's exactly what we used before. In the proposed approach, we have a bunch of extra terms. But again, no more degrees of freedom because we use polynomial representations of the S1 hat, S2 hat. And we need to calibrate 4 scalar coefficients here. And this is what it looks like. So the vanilla POD is given on the left, not particularly good. Approach 1, which is the POD-based representation learning approach, it will apply some curvature to the manifold, but it's kind of limited in what it can do. But in our alternating minimization-based approach, you are actually able to learn the basis on the fly. And what it will do is it will take that POD basis and gradually start rotating it to find you a configuration that's a lot more amenable to polynomial regression. So that's why it will kind of start lining up with the unknown solution manifolds. And obviously, the error drops as we put in more effort by directly tackling the representational learning problem. So this is a graphical representation of what the algorithm looks like. So we start off with a POD-based version of the approach, right, with the three basis vectors kind of lined up like that. And you will see gradually, the percussive problem, it will start applying these rotations and reflections in the basis to kind of nicely line up our approximation with the true solution manifolds. And we have a Jupyter notebook available that does all this for you if someone is interested. Okay, so we have talked a lot of math, a lot of nonlinear manifold stuff, nonlinear representations of data. At the end of the day, the thing we're interested in is really leveraging this in the context of physics-based computational models. And what I want to focus on is a framework that was developed technically in MIT by Ben Piershofer, who's now in Courant, and Karen Wilcox, who's now in Odin, obviously. So this is a framework in which we learn from the data by means of regression. And the only thing we have access to are snapshot data that come to us from the full order model, here given on the top for pressures and temperatures, and information about the structure of the governing equation that produced this simulation data. And then with the upper inference technology, we're able to infer these low-dimensional surrogate models that have the exact same structure as the original PDE model, but this has about 50 degrees of freedom rather than 500,000. And these approaches really work in a very straightforward manner. So we take a bunch of data, and from that we compute the POD basis. We then do projection of the data onto the POD basis to give us an S-hat. And then the whole idea behind this technology is that this structure of the reduced order model, which in this case happens to be quadratic, so we have constant term, linear term, quadratic term, we know that is the case because every physical system can be transformed by means of auxiliary variables to have this quadratic structure. So that's something we are going to exploit. And then it's just a matter of, well, you know what the structure of the reduced order model is. You're just going to try to fit a bunch of these operators, the C hat, A hat, and H hat, such that this whole residual is minimized. And it may not be obvious at first, but it turns out, once again, this is a linear least squares problem, which means that it's very scalable and very efficient to compute. We do apply some regularization typically to, again, avoid the overfitting. And what it does, it kind of penalizes the entries of these reduced order matrix operators. So with the nonlinear manifolds, we basically follow the exact same flow charts. So we have these nonlinear manifold approximations that we've learned, right, in the first part of my talk. And we plug that into a full order model that has quadratic structure. And then you end up with this mess. So the question is, what do you do? And it turns out, all these terms here, remember that the g's are polynomial, this whole mess really simplifies into something that looks very much like we've seen on the previous slide. So again, we have a reduced order model, which is low dimensional, that has that constant linear quadratic structure, but to that we now add something that accounts for higher order correlations in the data by means of these higher order polynomial representations. And then again, it's really business as usual. We have a reduced order model whose structure we know. We can minimize it, find operators such that this model is minimized in the least square sense, and then we apply regularization to each of these terms. So to give you a quick demonstration of the approach, let's go into some physics-based models. So this is the incompressible Navier-Stokes equation, right? So we're going to look at flow past a cylinder, which is a very well-studied problem in computational fluid mechanics, as well as in reduced order modeling. And we consider it at Reynolds number 100. So we have a finite element implementation of this, and we collect about 200 training snapshots in the time window 4 to 5 time units. When we do an SVD of that, we find that 8 POD modes captures about 99.99% of the energy in the system, which tells you that's really all the modal information, spectral information that you need. And the mean flow is your reference state, right? The state about which you're going to compute your variations. And then we have 8 POD modes where they come in pairs, so only have the first one of each pair because they have these alternating symmetry properties. But essentially, this is the modal information that you obtain from this data. Now, we built this reducible model using the POD here on top and our manifold-based approximations on the bottom. The training window is here, 4 to 5 time units, over which we collect 200 snapshots. And then the black lines is your solution from your large-scale finite element model. I think for this particular problem, we had about 300,000, yeah, it's right there, 300,000 degrees of freedom. So that's kind of what we're comparing this to. With POD, if you only use 2 degrees of freedom, that technically should be enough to really capture the dynamics of the system. You're really not capturing this vortex shedding behavior, right? The chemistry that you showed on the previous picture, it really kind of dies out after you exit the training regime. When you use all 8 basis vectors, technically all the information you have access to, it does really well in training. You kind of nail the response. But as soon, in a 5 to 6 time window, the oscillations will become unstable and your model blows up and, right, you don't really know what to do with that. With our manifold-based model, again, we have just 2 degrees of freedom. We train from 4 to 5 seconds, but after that, we can very actually capture this vortex shedding behavior in a stable way. And once we do the reconstructions in the original state space, where we kind of plot the vorticity, you can actually see that these are very accurate predictions. Obviously, you lose a little bit of information in some of the finer scale features, but the fact that we can do this with just 2 degrees of freedom is pretty incredible. So if we were to try to get better in capturing the finer scale features, here we only use quadratic embeddings. If we start ramping up the degree of the polynomial embeddings, we can actually do considerably better than this. Which brings me to my final slide. So what we've talked about today, we have introduced this very general framework for learning nonlinear state approximations from manifolds. We showed that numerical optimization potentially has a large role to play in identifying and characterizing these nonlinearities in data. We have shown that this can be integrated within a data-driven framework for learning physics-based reducible models. These models are human interpretable in the sense that we're just dealing with a bunch of ODEs. That's it. They enable rapid predictions. So these models allow us to make predictions outside of the operating conditions on which the model was trained. And finally, this whole procedure is non-intrusive. The only thing that we needed is a bunch of data and ideally information about the structure of the model that produced the data. And finally, we showed that we can do significantly better than standard POD/BCA, not just in terms of accuracy, but sometimes we even show that the manifold construction is actually necessary for producing stable predictions. So with that, this is my contact information for those of you who want to get in touch. We have a couple of papers out on the subject with more to come, and I'm happy to take any questions you have. Thank you.
Okay, thank you very much for your nice talk. A little bit technical also for me, but I try to understand.
I do apologize.
No worries. So I would first give the opportunity to our audience. If you have any questions, please do feel free to ask. Yes.
Thank you very much for the presentation. It was very interesting. At some point, you have a nonlinear system, or do you?
What do you mean nonlinear system?
Like the system that you're trying to surrogate is linear or nonlinear?
They're all nonlinear problems, yes.
And then you, when you optimize it or when you fit your model,
right,
then you don't do any iterative optimization there. You do like a single value decomposition there. How do you capture the nonlinearity?
For the approach. So the reduced order model is nonlinear.
Yes.
Right. So we have this quadratic structure, so that tells you it's nonlinear. In the upper inference part of the approach, you still have a nonlinear representation of those system dynamics. But it doesn't mean that the optimization problem itself becomes nonlinear. Because once you have the data, or its quadratic representation, this amounts to just linear least squares. Despite the fact that the problem, and potentially even the approximation, everything is nonlinear, the inference is still linear.
Okay.
But great question, though. Thank you.
Thank you.
Hi, thanks for the presentation. Coming from a chair where we work a lot with physics-based models, I'm struggling to see where physics are involved in these representations. I mean, I keep seeing operator inference. I'm struggling to see where you replicate physics in a reduced dimension.
So we do not explicitly exploit, say, gradient operators or whatever structure that your PDE model may have. But what we do know is that all these systems, whether it's a heat equation or Berg's equation or any nonlinear problem, those systems can be represented in quadratic form. So that is this model structure. So that is, even though you do not know what the operators are, or you do not have access to them in a, let's say, finite element implementation, that's not what we need. We need to know the structure of the reduced order model that dictates this.
Fully understand that. I'm still not seeing how is this physics-based, though.
That is the physics. So if you were to do a linear problem, you do not have this additional quadratic term. Whereas if you do Navier-Stokes, which has inherent quadratic structure, you do need it. So that is how we tie it back to the physics.
Thank you a lot for the interesting talk. I actually have two questions. The first one is, if I understand your second approach correctly, you use the POD as a first estimation and then use the minimization procedure to update the tangent space. My question would be, so because POD is like you identify the space to a fixed point. Correct. So I'm wondering if this, so in the reduced order model it produced, the origin will always be contained in this manifold you mentioned. Yes. And yes, so that would be my first question. Why do you, is it limited somehow because of this mass basis? And my second question would be, because I'm aware of some other like model reduction techniques for, which like other examples also used the, for example, the vortex shedding you showed, okay. For example, Cindy. I'm wondering what is this method, what is the advantage compared to other model reduction techniques? Thanks a lot.
Okay, there's a lot to unpack there, so let me give a second. So when you talk about reference points that are used for computing the SVD, we still have that. For instance, if you want the manifold, the nonlinear manifold, to go through this reference point, you should set all the coefficients to be equal to 0. And then your state is exactly equal to your reference point. So nothing really changes there compared to what we have been doing with POD or principal component analysis. So I'm not sure that answers your question there, the first one at least. we can talk afterwards. For the second part of the question, like a SINDI type approach, with SINDI you have a reduced state representation of the data, right? Whether it's POD coefficients, and from that you then try to identify the dynamics which are relevant for kind of capturing that vortex shedding behavior. That's not what we do. We learn the structure of the approximation using the manifolds, and then we plug that in to the structure that we know we have for Navier-Stokes, which happens to be quadratic. So all those things combined give me a ODE, which has polynomial structure, just like SINDI potentially can have if you consider polynomial terms in your library. But SINDI does not exploit model structure. It learns from data the way that this approach does, but in our approach, we exploit the structure of the PDE model that we know plays an important role in the dynamics of vortex shedding.
Yeah, thanks a lot for this interesting presentation. So there's an underlying assumption here that the trajectories that you're training on lie on an invariant manifold.
Yes.
And it'd be interesting to hear your perspective on how do you know the dimensionality of that manifold. For example, is it unique? Does it exist? You know, under what conditions is that assumption justified?
To be honest, that's way beyond my expertise. I can't really, I'm not a dynamics expert, so I can't really comment on how to infer dimensionality. I do know that a lot of this is really dictated by the singular value decay of the problem under consideration. But the thing is, for our applications, we don't really care. We just know that we have to build a physics-based surrogate that is computationally tractable to evaluate. And even though the manifold may not be intrinsically low-dimensional, we still try to get as good an approximation as possible. But we have no guarantees, or we have no way to demonstrate uniqueness or make a better choice about dimensionality than just looking at the SVD.
Right, so you may be familiar that there is some work out there in the field that actually goes into the existence and uniqueness
I know about
of
George's
these.
work, yes.
Yeah, exactly.
Yeah.
And the other question I have is about the vortex shedding. I see that you're training basically only on a periodic orbit.
Sure, yes.
Right. So couldn't you use a one-dimensional model then?
A one-dimensional model?
If you're only interested in this, basically the period of this periodic orbit, I mean, you could use a sine function with the same period as the response and then fit a map from that signal to the full phase space.
That could be possible, for sure. My understanding of the literature is that there's really only 2 degrees of freedom that matter, and all the other ones are potentially a slave to those 2 active degrees of freedom. Potentially, if you do some kind of variable transformation, you could express it in terms of a sine, because it is cyclic, but we have not looked into that. But technically, you're right, is that, 1 degree of freedom should do. But considering the polynomial structure we have, so we don't deal with any harmonic or trigonometric functions, that's not readily clear how to do that in our approach. But technically it should be possible, I agree.
So I think that in order to fit nonlinear terms in the dynamics, you would probably have to look at the transients approaching this periodic orbit.
Right.
So, okay. Yeah, thank you anyway.
Thank you. So we'll have one more question,
okay,
and then the rest we'll leave for discussion.
Yeah, thank you very much for your talk. It was super interesting. So on the last slide where you showed with the vortex shedding, and you kind of used data from the, so I guess with the grey window, that's where you had the data.
Correct. Yes.
And then you're projecting and extrapolating for the rest of it. So the motivation behind this is to have much more efficient modeling for things that you want to model rather than running like really expensive computational things.
Mm-hmm.
In this case, it's sort of, you've given it a kickstart with data and then you're extrapolating from there. But then in application, we're going to want to usually do it by like changing system parameters and then rerunning the model.
Yes.
What are the next steps to go from here to that sort of place? Because if we don't have a physically meaningful knowledge of the
that's a great question, and it's still a little bit of an open problem, would argue. There's things that we can do right now. For instance, you change the initial condition and kind of see where it goes. But to really properly account for the parametric nature, for instance, this was trained on Reynolds number 100. If you want to make predictions about Reynolds numbers 200 using data only from the 100 model, what would that look like? You would definitely have to change formulation to properly account for that structure. You can brute force a little bit by doing some kind of interpolation of the bases on Grassmannian manifolds, which is a whole bunch of other literature. But to really do it in an integrated fashion is still a little bit of an open question, especially when it comes to these nonlinear state approximations. So I agree there's still a lot of work to be done, but yeah, we're not done with this yet.
Can you, so on the equation you had that you were maximizing, and that is a arguably low level of physics restriction, as with what Kostas was concerned about, with the fact that it's not the exact PDE, it's what you said, that these systems can be represented on a lower manifold using this equation, right?
Right.
Can you change that equation to embed a known PDE, and then you can use that as like a physically representative lower space manifold?
Assuming that you explicitly want to have the PDE in there, granted the fact that the PDE is likely going to be nonlinear, you're going to need some additional techniques to deal with, they call it hyperreduction, to essentially account for the nonlinear terms, because otherwise you won't have any computational speedups. So there are ways of doing that in that kind of a setting, but what we wanted to do is completely be hands-off, fully non-intrusive. We do not have access to any of the nonlinear operators, which are finite element-based or whatever. But yes, you could certainly explicitly take Navier-Stokes, reduce it by having these approximations and do it that way. But that's not what we were after. Our focus has been fully non-intrusive and only have insights into the structure of the equations. So that's what this does. But it's a completely valid setting that people have been doing research in. That's just not something that we talk about today.
Okay, great, thank you.
Okay. Thank you very much. From what I hear, we have quite a variety in the audience of different research backgrounds, and that is very nice to hear. And I think we can exchange more during our apéro, with which I would like to start now. But first, 2 closing slides. A short outlook on the next presentation. This will be held by Professor Dr. Katrin Dörfler from the Technical University of Munich about collaborative construction, which is quite a wide term, and we're excited to see what she will present to us. And with that, we're at the end of today's seminar series. Thank you very much for joining us, and hope to see you another time again.
Thank you.